Okay, here we are again. synSpace drone runners for Android, available for Kindle Fire and in the Google Play Store. In the videos leading up to this one, we identified an issue with the vocoder that it was not. So this is that issue where I have noise so long as I have my USB connection. So if I disconnect my USB cable, that noise goes away. Weird. So now we're recording right now, but there's no data coming in yet. And normally we would record actual data, from the microphone. But what we're going to do is turn on this new test feature that I added. Nerd info, blah, 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 show debug info on. And it changes various things. You wouldn't want to keep it in this mode probably. But like if you touch the screen, it shows where you touched. If you drag, it sort of shows you that. If you do several touches, it does that. So that's kind of fun. Ooh, look at that. And you can see that I only track 5 touches. Anyway, but again, we had this weird problem where my filter response wasn't the same across the entire scale. But now that I've turned that debug mode on, what's happening is it's still recording stuff from the microphone, which currently is silence, but then it's overriding it with mathematically generated perfect sine waves. Let me get that back on screen for you. So it's just stepping through every note in the range that I'm trying to be able to analyze, and you can see it's got a perfect signal for every note. Now it's flipped back to the low notes, and so it's got nice and wide there. And if you just look at this filter response here, you can now see it's very, very consistent for across the entire keyboard. If you look at the maximum, this thing called max 50 meg, that's basically the measurement of the tallest peak of all of them that you see on screen right now. And you see, it's just, as we're sliding across, it's just staying rock solid at 50. And that's fantastic. I mean, I'm giving it a perfect input signal. It should be rock solid, but before that was not the case. Now, notice the waterfall or the pachinko table or whatever. I changed this color here from that Midland gray to this kind of neat ombre from black to red. As energy passes through the sieves and becomes more and more clearly identified as a note, then I make it a more exciting color. But then when it actually shows up down here, when I've selected the note, the color I'm showing is the rainbow color. So C is red, and E is yellow, and G is sky blue. So it's kind of fun to look at what these shapes look like. If you look at these in rows, right? So the row just above the piano keys row, you can see it also has this same bell shape, and just much flatter, mainly because I'm rendering it so squished down. But it's only a couple of bars, right? And what ideally, each of these notes belongs to exactly one of those boxes. And so if I'm only generating one note, you might think, well, why are you lighting up more than one box in the row above? And you're right, and I can raise my Q value and I will light up fewer boxes, but I found that when you're getting close to the edge, where a lot of these boxes are going to kind of change at the same time, it's kind of natural that the energy can't just move completely from one box to the next. And so what ends up happening is, as it crosses the boundary, the energy in the departing box starts to go down as the energy in the receiving box starts to go up. This row is pretty easy. Like that one will start to fill now. Okay, now it's the dominant one, and that one has started to fill, and then it went away. It was filling for a while and then it stopped. Anyway, so I needed to have enough slop in the queue for these guys so that I don't get into situations where for just a moment a new note that's just crossed a line is like invisible. It's like it doesn't quite get enough energy poured through to be considered a note. Anyway, so the chord rainbow is also showing this. At the very bottom of the chord rainbow, this little white, ooh, don't touch things, this little white bar, that's just energy. That's how loud it thinks it is. And this is very loud. This is a very loud signal. It's a very strong, powerful, clear, loud signal. So you can see it's just a loud bon, 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 bon. But its pitch is changing, and so you see it nicely going up through the rainbow all the way to the top and then back to C. So every octave it goes back to C, red, and then works its way up to B, purple, and then falls back down to C. And the bar you see right now is the bar that's just appearing here. There's a little missing time. Anyway, so this did not look this good. Now it looks great. So kudos for having quality test patterns. But now I've seen it. I'm happy with it. I can turn it off. Bonk. Okay, and now I'm back to just recording what's really there. Anyway, so you can turn that on and off by turning on the debug info, which turns on other things, but the game itself is probably fundamentally broken in some way when you're in debug mode. See you in the next film. Now, while I am doing this, we're also doing some science. And today, the definition of science is to run this online tone generator. I'll turn on my speaker. And I'm going to play, that's E3. Okay, so my computer, which is over there, is playing. I'm going to plug this magic cable in again here. Okay, I'm going to turn this down. You get the idea. So I'm using this website called Online Tone Generator. And if they ever ask for $1, I will send it to them because they've been very useful. But I've gotten some measurements to make me wonder whether or not there could be some problem in my signal path where I have some resonant frequencies that are interfering with my ability to vocode. So with that being said, let's switch to the vocoder. I turn the vocoder on, turn the vocoder off. I'm going to start recording. Okay, now I'm recording. Anyway, but this is what happens. It's listening to a single frequency coming from this online tone generator, and the frequency it's sending out it thinks it's E3, and so if I claim that's C4 and that's C3, that therefore that is in fact E3. So, woohoo! Thank you, international standards. And if you look, I have about the side frequencies, the frequency a little to the left and a little to the right of E3, which are in fact E flat 3 and E sharp 3. Okay, now we look down here. This oscilloscope, which looks all terrible, this is what's actually coming in from the microphone. In this case, it's coming in from the magic cable from my computer. So this is the source signal coming in from online tone generator, and you would say, oh, they're doing a bad job. Look at what a horrible tone they're doing. That's got to add all sorts of side frequencies, and look at the rate at which the fall off goes and how broad the bass is for this one note. It's natural for it to look like this a little bit, but that's pretty broad. I mean, I'm still handling that great. There's situations where I don't handle it great, but this noise is kind of like, okay, that's fine. I have to be able to deal with that sort of thing in the real world. But right now, in the laboratory, what I really want to do is make sure my math is all right and that my filters are all doing exactly the kind of filtering I want them to do. So for that, I want to be able to give it a perfect signal. And my solution to that was in software, I just set it up so that instead of using the real microphone data, I used perfect data that I would compute mathematically on the fly. You know, I use sine wave routine to find, you know, the next perfect value. And I did that during early development and turned it off because that's a compile time thing. So it's, you know, you got to build the whole thing one way and then test it and then build it all a different way and then test it and build it all. And, you know, it's kind of no fun. But anyway, so I was really sad about all of this noise coming in when I used my cable to record from the computer. But I thought, oh, well, you know, noise on signals. And my setup here uses really long cables too. So it's like, I'm going to have noise. But then I finally realized that, turn that light on so you can see that, the USB cable. If I disconnect the USB cable, and the sound is not coming in from the USB cable, but the USB cable is providing some sort of a ground current loop that's picking up all that noise and is injecting noise into the whole tablet, which is then also seen in the, well, I won't presume to explain the actual phenomenon, but look how much cleaner it gets when I unplug the stupid USB cable. And it's only, this USB cable goes to that computer, the same computer that's providing the audio. So these are both providing ground from that same computer, but through two very long different paths. And I think that's the fundamental problem. Okay, but now you're looking at this and it's still a little wobbly, right? You know, is that just mean? I mean, I'm trying to sync my oscilloscope, and this oscilloscope is not smart enough to pinch zoom and stuff. So I was kind of thinking today of tricking out this oscilloscope a little bit so that I could get the scientific value from it. But I think the argument you could make here is that the online tone generator really is about this amount of wobble in it. It's not my lying. And if we move around, like we go down to E2, this is very close to our limit of recognition, but we're still getting a good signal. So this signal is working great. But check this out. What is that all about? See how there's a little jaggies? That could just be a display artifact because I use a buffer over and over and over again. And it could be that when it's rendering it, it may be rendering past the newest data and into data from the previous loop around. And that's what it looks like it's doing, in fact. So that could be happening in the online tone generator. But honestly, if you just listen to it, you would hear that. So I think that's just a display glitch, another reason why. In fact, you can kind of tell here that we're sort of seeing two images. I don't know. Anyway, it could also be basically a flaw in my trigger logic that when the signal gets smaller, the signal here is considerably smaller. Notice that it's at 2000K. If I go back up to E3, the actual energy is 5000K. And so it's twice as much energy, it's twice as big a signal. And so my trigger detection, the thing that's trying to synchronize the waveform so that it is not just randomly jumping all over the place. So you can sort of compare two passes of the waveform in a row and say that, well, it looks like maybe there's this much of a delta between them. But if the trigger point is moving up and down that same amount, which it might be, it's hard to say, then that would just be a false clue also. But the point is, E2 is a little marginal, but still pretty good. C2, okay, C2 is unacceptable. D2, so C sharp 2 is the lowest I even try to go. And notice I'm only getting 1.7K, well, 1700K, but look at what a nice little signal it is. It's a good little signal. It's pretty. And then I go to D, and it goes up to 2700, and still a good signal. And then I go to D sharp, still a good signal. And the energy is slowly going up. And this signal is getting a little less good. Okay, now we go to F2. And look at that. Look how Look what a hard time it's having. And we look down here, I mean, well, basically, look at the loudness of the signal. It's dropped down to 500K. It's just a tiny signal. And when it's at 500K, it's oscillating, it's going back and forth. When it's at 500K, we're screwed. Okay, now, if we look for insights into it from the binary search algorithm, it could be that something in my algorithm up here, which I've been messing with lately, is deciding that a higher order filter did not have enough energy in it to justify looking down low anymore. And for right now, I'd say that's a pretty good guess. Like it's got a critical... You can certainly see that there's a beat frequency going on, and so the signal really is changing in size. So it's possible that my reaction, though, is correct. It's changing in size and it's dipping below my threshold. And now if I go to the online tone generator, but you see, the thing is, I don't know, I still don't know, is online tone generator making a lower tone? Well, I guess I can do that this way. Between F2 and E2 to talk about... Oh yeah, let's go back to that scientific experiment we were in the middle of. So we're using the vocoder, using the social key in vocoder mode, where we have enabled the vocoder here in general by saying show vocoder in social. That icon there meaning vocoder as opposed to piano. And text chat. Whew. And we've got the vocoder in piano mode, and we go to record at +3 dB mic preamp, and then we've got our magic cable plugged in, so we're getting a signal from my computer, and this is that same signal we were looking at before, which is F2. Okay, and as you can see, it's kind of coming in and out of existence, and as you see down in the little oscilloscope here, the main problem is that the signal itself gets small. Something is causing it to toggle between louder and softer. And when it's small, it's a little too low of energy for us to perceive it. Now, it's still coming in at just under, I'd say, 1600K. So I think that counts as a bug, because I'd like to be able to record at that low level. So I'm gonna address that by using the mic preamp and knock it up until that stops happening. So up 1 dB. Oh, that didn't take long. So this is just a preamp, a pure preamp. It takes whatever the signal coming in is right as soon as it comes in, from the microphone, and it scales it a little bit right then and there, and then no additional changes are made after that point. In theory, it's the same as turning the volume up on the computer in this case, and to be clear, I have the volume down pretty low because this is a pretty intense sound if you're actually listening to it through speakers. But you'll notice that while it's not winking in and out of existence anymore, it still is oscillating between several amplitudes. It's just that the low amplitude is no longer too low. So exactly what that's all about is a little interesting. So let's go up another one, +4. Let's go up +5. And we still see the beat frequency here. And that didn't really improve that signal. Let's just go up all the way to +9. And that particular signal, not particularly additionally improved. Oh, actually, you can see all the noise here. I've still got it connected to the USB cable, so if I get rid of that, then that makes the actual recording, gives it a chance to be smoother. But here you can see it doesn't really look all that smooth. So at +3, we had a problem. At +4, the problem went away. plus 5 plus 6. Problem is still gone. Let's just try that. So now let's try it all the way from C2, which is just below our acceptable range, C sharp 2, our first note. And by the way, notice that on the scale, that's around the second note of the scale, and the colors are Roy G. Biv, red, orange, yellow. So it's headed into the orange. You know, C is red, orange is C sharp, D. Anyway, so D2, and D sharp. I'm getting into yellow. F2. That still looks about the same yellow to me. I'm sorry, that was E2. F2 is greenish, but notice again the shoulders, the sidebands, are very close to the peak. Ideally, we'd like to see a much sharper edge. F sharp. This has been a traditionally difficult one for me, but in this case, look at how nice that looks. That's what we want them all to look like. So these two notes, very close together in frequency, but mathematically coming out of the filters with a very different response. And if we just look at the amplitude, the bad one is 3100K, and the good one is 4,000. Okay, so there is a difference. And if we look down here at the sine wave, and again, this is technically what we're getting in from the microphone. So these little wiggles of noise here, those are real. These little flashes of noise over there, try to ignore those. Those are just the way I render things. But the individual little squiggly wigglies, those are real levels of noise. Now if we go again, we go to a good signal. It's got the same level of wiggly squiggly noise. So it's not perfect, but it's probably not really relevant. So I can't explain why the side lobes, you know, that typically would imply that the frequency is jittering, that in addition to being at its center frequency, it's going up a little, down a little, and it's providing resonance at the adjacent semitones. So I've got a problem, and I think it might be in my magic cable. But we keep going up. F sharp, that looks good. G, that looks real good. G sharp, that looks good. A2, okay, so A2, not so great. So G sharp, good. A2, not so great. A sharp, okay, not great. B2, great. So A2 and A sharp 2, both a little compromised. And if we look at, well, that's all we can do. Okay, so we go to B2, it looks good. And B3, fantastic. Now again, so long as the online tone generator is doing exactly the same amplitude for all of these frequencies, and so long as the wiring between the computer and the magic cable to my tablet is not preferentially distorting certain frequencies, you know, if it's not resonating at certain frequencies, which it might be, and which it likely is, I should be able to get, from my math, I should be able to get pretty much an identical looking spike for every single tone along the scale. And I'm suspicious that I still show this much variation. It makes me feel like probably there's something I'm doing wrong. Okay, so anyway, so we switch to C4, middle C, and look at that, it's kind of close to unacceptable. So that should be a fantastic looking signal. If you look up above, often when the signal down here is kind of squirrely, it's sort of because it's, well, not because, but it's coincidentally or not, it's close to one of these important boundaries in the energy up here. Like right there, there's an important left-right boundary. And it's like a gray code almost kind of question of like if more than one bit changes as you move a little bit across the line, it's like somehow when you are at a frequency where that is true up above, it seems to reflect itself down below as getting sort of a weak filter response. Now, what I haven't been saying is it's possible that the math of the filter, for whatever reason, fails at certain resonances. Like if your sampling frequency is 16 kilohertz, maybe there's a handful of frequencies that just that filter ends up behaving poorly at. But you know what? I can totally test that. Yes, that's what I'll do. I'll put back in that code that does a synthetic recording. Instead of looking at what you really recorded, it just makes a sine wave of the perfect frequency. And then I'll make it sweep all the way back and forth slowly. And then it should look perfect because it will always be the right amplitude no matter what, and it will always have perfect pitch no matter what. It won't have any noise in it. And all the filters will have been configured perfectly for their particular frequencies, and if anything looks weird, that will be educational. So I have to do that. Anyway, so to achieve my goal, it's not going to be done by tricking up the oscilloscope. It's going to be done by putting in my old test code and just giving my new filters a good workout. And I'd like to have it sweep over the entire frequency range, and I'd also like to be able to test it at different amplitudes. So hopefully my little mic pre-boost actually will get applied to this stuff as well. Okay, well, so I think this is a good time to stop the movie and write a little code and then come right back. Okay, back again with synSpace drone runner demo test whatever. Again, still looking at the music. And this is a special build now that while technically I'm in music mode on the vocoder and I'm recording, it's going through all the work of getting the information from the microphone, or in this case from the magic cable, feeding it from my PC. But I've been throwing away the samples that it really got and in replacing them with mathematically computed samples of a perfect frequency. So you see this is a perfect sine wave. So, and then it continues with the regular math that I would normally do for incoming stuff from the microphone. So now, and it goes through the entire keyboard and then flips back to the bottom. It doesn't bother to do the regions outside my, 5-octave keyboard, synthesizer keyboard. So these are perfect frequencies, perfectly tuned to the center frequency of each of these filters. And what I would really like to see is I'd like to see these little peaks here looking the same for each one. But as you can see, it kind of goes through a little. Okay, the peaks are getting really good, then they're getting worse for a while, then they're getting good again, then they're getting worse for a while, then they're getting really good, then worse. Okay, so I think that's really suspicious. I think I need to pursue this until I can explain why that doesn't just always look the same. And I think also, because I'm always giving it the exact same height here, this is a good way to make sure that my math equalizes the amplitude properly. Because you do get a different energy just by the fact that this cycle, at this frequency, you're only seeing a couple of repetitions of the wave period. Whereas at higher frequencies, you're seeing many more repetitions of the wave period. And I think you would tend to get better consistency if you were always measuring a fixed multiple of the wavelength. So it's like no matter what the frequency is, I would run exactly n periods, where n was the same number for all frequencies, through my filter. And then I would have some easy correlation to get a balanced energy reading. Because I basically, this reading here, that's now down to 10 million, it goes between 500,000 and 20 or 30 million as you go across the spectrum. And again, I'm giving it exactly the same height of a sine wave for every frame. So aside from resonances in the cables and inside the tablet itself, I feel I should be getting a very consistent picture. Now the chord rainbow is nice. I mean, it's showing, it's detecting the notes nicely, and it just goes up and through them. Chord rainbow only shows 1 octave, so every time it hits C, it drops back down. So, you know, that's working pretty well. So I'm not complaining with this level of functionality because I'm really proud of it, but it still strikes me as highly suspicious. I can't explain those regions where the signal is not as good. But I'm pretty proud of this data here. I think this new forced sine wave stuff, which I had to totally rewrite. My original one was way too primitive. I have seen issues with the trigger limit of those guys. I think I'll change that a little bit. I'll lower the limit. That'll tend to make it a little slower though, because it'll tend to err on the side of making more energy measurements as opposed to fewer. So the way these biquad filters work is you have to, there's some constants inside of each filter that you have to manually set ahead of time to set the filter up to behave a certain way. Let's explore my actual computation of energy. Maybe my definition of energy is flawed. Okay, see you in a bit. Okay, so here I have redefined my measurement of energy and diddled the energy to follow through the pachinko filter here. And now, look at those side lobes. I mean, they're non-existent. It's just pure frequency detection. Look at the chord ribbon. It's now getting the beginning and the end of every note. It's got the full width of every note. It can go through the whole spectrum, and it's a beautiful little king peak for each one. So what was happening before was I was doing two things, and I'm disappointed about one of them that I've just turned off. Because this was one of my huge steps forward a few months ago, was I realized that I got much better spectrum data if I fed in an exact number of wavelengths of the signal. And this removes all that code, and I'm now just sending through the most recent 160 samples, no matter what the frequency is. And it's giving me a better signal and a more consistent signal. Now I'm giving it a perfect sine wave of a fixed size, but it's translating that into this 7000K, you know, over the entire spectrum. So it's very even. So now I got to turn it off and see how real data works. I may have to change my default gain here, this plus 3 dB on the mic boost. If I take that down to 0, logically it should cut it in half. So it should cut it from about 8 million to about 4 million. But it's actually 1, 2, 3 going to have a different effect than that, I think. Yeah. So depending on how that bugs me, I may do something about that. But on the other hand, it actually gives me a much wider range to work with. So I don't know. If this works, I may just go with it. Yep, that's looking really, really, really good with this perfect data. So now I guess we'll go back to real data and see how much worse it looks. So I could actually do that in front of you. This was in audio, I think. Is it in audio or is it in sound? It's in audio. Okay, so I can turn it off by changing that true into a false. And then do new build deploy. And we'll have to do some basic gain experiments to see what's going on, but mic boost is what that's called. Yeah. So I've been defaulting it to 3 dB, a positive 3 dB, and I may just default it to 0 dB if it ends up being too loud right now. Okay, so we record and right, there's nothing there now. So let's unplug this. Hey there, I'm talking and stuff and junk. Here, let's unplug this. Let's clear that. Stop that. Go out of music mode. Let's see how much. Hello, I'm speaking in a theatrical voice at the old amplitude. And it looks quite different because of the new filters. And the amplitude 10 meg. Okay, that's actually not all that bad. Okay, and now we play it back. Well, I don't know. That's not too bad. Go to music mode. Now we sing a song with notes in our song. Okay, that's pretty good. Okay, so we're in music mode. Let's go back to our recorder music and see what happens. We lost it. YouCanPlayIt.com. Oh, sorry, gotta plug back in. Okay, I have to go up a bit for this. Okay, so we'll go up to 6 dB. Well, I think that's still a little too fast for me. Let's try a different song. I tweaked my Q values the other day, and now I kind of would like to have a lower Q value. Okay, Swan Lake, stop. Okay, now we're launching a new build. And the change in this build is I lowered the Q values for the 2 bottom rows. Yeah, the bottom rows that were failing. So yeah, that makes good. It's probably going to be good. Okay. So silence still looks like silence, and we'll disconnect again for the noise, and then we'll play the music. And how's it look? Okay, I'm gonna stop this now and come back when I've got it working. Okay, I've done some more monkeying around. Let's see how we're doing. We're gonna make a new recording of Swan Lake. Record for music mode, vocoder on, play the song, record the whole thing. Oh, and I'm at plus 9 dB on my preamp. And look at these insanely sharp peaks. I've been lowering my Q considerably and still getting these. Now my frame rate has dropped to below 35 frames per second. Well, that's actually okay. The samples are coming in at 25 spectrums per second. So if you drop below 25 frames per second, you probably are falling behind in the vocoder stuff. Okay, so let's just listen to the spectral playback. Well, let's adjust it to more or less to start the song and play it back. So even at plus 9, it didn't get all the notes. There's still something fundamentally screwy about that. But we'll throw those samples away and we'll play back the actual groove, which looks like this. Here it comes. Well, so I'm not happy with that, but I feel really close to being happy with something. We're going to record the slow version. Again, new track. Okay. Oh, I'm not plugged in. I want to see if the notes I missed are because I didn't like that one. That was a frequency miss. It's very noisy. It can't figure it out. It's going back and forth between several notes. I think if we look down here, we'll see that the signal looks noisy. So F sharp and G are the problem areas again. And I know now that if I had a perfect signal, I would get a perfect wave. Is that just vibrato that's messing me up? Okay. I gotta screw around some more now. Okay, so I fiddled around with the... Okay, I made a test mode where I could provide absolutely perfect sine waves swept along the entire spectrum to test my individual filters, and I found that they were not always the same width. If you looked at their sidebars, their sidebands, they didn't really have a similar shape, and they really should have all the way across. And so when I looked into that more, I found an optimization I did earlier in the year that I thought was really great. When I took that out, that problem went away, and I now have a very sharp signal for every note again. Okay, but then that changes the actual measurement of energy. So I started looking into that, and I started realizing that the way I was computing energy is maybe not the smartest way to do it. So I did it a new way, and then that caused some ripples, so I had to go back and forth and rebalance everything. And so I'll probably still be rebalancing it for a while now. But I like it a lot right now, and here's a spectral recording of Stairway to Heaven. Hopefully this is a fair use and nobody will complain about this quality. My speakers picked up a buzz today as well. I may have gotten more bass as part of this. Well, I'm sorry, but the speaker cracking is bothering me. So I'm going to delete it. Goodbye. It sounds really nice in the earbuds. So now we'll play back the groove it left behind. And I'm secretly hoping that this is actually pretty good. Okay, I guess I should be a little honored, but I got a takedown notification from YouTube because this section where I basically play Stairway to Heaven on my own synthesizer with my own sequencer, making every single little sample myself, is in fact apparently not allowed. So apparently if I were to sit at a piano and try to just play the song, that also would be not allowed. So I don't want to fight it. I think it's fair use, but it's a beautiful song, and I clearly don't, I benefit from it being a beautiful song, and I don't want to take anything away from the song. So it was a very nice performance, and you'll just have to take my word for it. And it also complained about Swan Lake, so I'm not quite sure who owns the copyright to that at the moment, but I'm going to similarly obfuscate that, and hopefully that's what I'm doing. La 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 la. But I left it a few seconds at the very beginning, which was I think less than 7 seconds, which I think is like, okay, I gotta stop now. Okay, bye. Okay, well that was fantastic. So we will go ahead and clone this again. And we're just calling this Stairway. So I'm keeping around a bunch of old samples so I can track quality over time. Okay, so this is that test code that just feeds in pure sine waves of exactly the right frequency and then steps through the entire 5-octave synthesizer span. There we go. So also look at the waterfall or pachinko display up above, and it's kind of hard to tell with the gray, but you can see that there's a little bump following the line, and that bump is about the right size for the square size on its row. So I'm not including too many extraneous notes, and I'm not getting too close to the edge of filtering anything. So if the ultimate success is if you look at the little line down at the bottom of the line, the debris on either side, the total width of that is about 8 notes, whereas before it was about 30 notes. So that's kind of like the overall measure of the precision of the sensing. And then of course the fact that there's most of the bar has no shoulders at all is just excellent. It's funny, it looks different on the camera because the phosphors of the display, I guess, or phosphors of the camera, I guess it's the camera chip itself that's glowing. Anyway, it's actually kind of diagnostically useful. So anyway, so this is about as good as we're ever going to get the filters to work in a test mode. So now I'll take this off and go back to real mode. Yeah, that looks pretty good. I like that. a lot of tweaking there.